सर मेरी आ रही है? Assalamu alaikum and very good morning, ladies and gentlemen. Starting with the name of Allah, the most merciful and the most beneficent. I am Farwa Javed from the Department of Computer Science, Lahore Garrison University. A warmly welcome to all ladies and gentlemen on fourth National Conference of Computer Science and Information Technology. Let's call Hafiz Yaqub so further to recite a few verses of Holy Quran. Please join, sir.
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم رب المشرقين ورب المغربين فبأي آلاء ربكما تكذبان مرج البحرين يلتقيان بينهما برزخ لا يبغيان وبأي آلاء ربكما تكذبان وله الجوار المنشآت في البحر كالأعلام فبأي آلاء ربكما تكذبان يخرج منهما اللؤلؤ والمرجان فبأي آلاء ربكما تكذبان وله الجوار المنشآت في البحر كالأعلام فبأي آلاء ربكما تكذبان كل من عليها فان ويبقى وجه ربك ذو الجلال والإكرام وبأي آلاء ربكما تكذبان صدق الله العظيم.
Jazakallah, sir. So, ladies and gentlemen, this is our conference day 2 and session 1. Let's call our first speaker, Dr. Nasheen Sabahat. She is assistant professor at Computer Science Department, FC College. She did her PhD in Computer Science, Software Engineering from NUST, Islamabad. Her PhD thesis was Software Science Estimation of Border-Based Desktop Game. Her research areas are Software Requirement Engineering, Software Size and Cost Estimation, Software Quality Engineering, Empirical Software Engineering, Software Project Management, E-Learning. She is the author of many research papers for Impact Factor Journal, hands-on experience with regression analysis using statistical software tools. So please join ma'am, Dr. Nasheen Sabahat.
Assalamu alaikum. Thank you so much, Farwa, for such a nice introduction. I will start my talk. Let me share my video first. Let me share the slides. Okay, I hope you can see my screen now.
Yes, ma'am. Please continue.
Okay, thank you so much. Okay, so the topic of my talk is somewhat related to, it is different from the research that we do, and it is related to somewhat industry. That is the future of development that we are going to see in the coming years. That is cross-platform development. This is the outline of my presentation. I'll discuss the difference between the native applications and the cross-platform development, and which one to use in which case, and then which one is the best option, and the frameworks of cross-platform development. So as we see that the mobile application market, it keeps on growing, and it is unlikely that anything will significantly change in the coming years. We are using technology from past many years, and we will be using it in the next years as well. So at the same time, we can see that 99% of all the smartphones in the world, they work on one of these two platforms, either iOS or Android. So development of hundreds and thousands of applications are there everywhere, every day. Entrepreneurs, there are startups, there are independent developers, there are some freelancers, they produce many applications every day. However, anyone who is going to develop these applications, they have to choose either from these two options. Either they have to do the native development, or they have to do cross platform development. But these approaches differ in a number of features from one another. So let's explore what is native apps. So native application is the one which is built on a specific programming language for the specific device platform. It will be either for the iOS or Android. So the simplest example can be that of the any basic program that you see every day. So it is actually that program which is developed for use on a particular platform or device. So it has then the ability to use device specific hardware and software. It uses the programming languages and development tools that are native for any particular operating system. For example, we see that the Swift or Objective C is used for to write the applications for iOS, whereas for Android, Java is usually used, and Kotlin is also used for Android. So as all other applications, it also has advantages and disadvantages. Whenever you create native applications, there are no restrictions on the performance and speed. And we can see that this is very, very important for some types of applications. For example, there are applications which have lots of graphics. So then we have to see the performance and speed. And then the second thing that we see is that the user interface elements are very familiar to the platform user. So in that case, the user will provide high quality user experience. It will be provided, the high quality user experience will be provided to him. And another thing is that because there is an access to all the smartphone functions and operating system functions will be available to it. That is camera, microphone, geolocation, accelerometer, all of these functions are available to it. And new hardware and software functionality is also available whenever it is released. And then there is an availability of large number of control tools, which speeds up the testing process at the developer end, and it makes it more convenient for him for development. And there is a high level of integration with the platform. The development is carried out using the technologies recommended by a particular operating systems developer. So it gives you the right once approach, that is right once, right anywhere approach. Sorry, it do not gives you that approach. It gives you the flexibility of performance and speed with itself. But when we want to see the right ones and right anywhere approach, then we will see the cross-platform development. Okay, there are some disadvantages also associated to this native application development. there are no if its presence is required for both iOS and Android, for example, for any application, then you have to create two applications, so which will significantly slow down the development and testing, because you have to develop the application for iOS and then you have to develop it for Android, and then you have to do the development and testing for both, so which will slow down your process. So if you want to do faster development, then you will not select this native development. And then secondly, you have to do separate development for each platform, which will require more specialists. For example, you have iOS, Android, you have Windows, so you have to do separate development for the same application, and that's why you will require more and more specialists. It will increase your budget, it will increase your time. And the third thing is that you will need to monitor applications for every platform that you are going to develop the application for. So this will also require more time and more resources for the technical support. So let's see. This all of these disadvantages were taken over by the cross-platform development. To overcome the issues, this idea of cross-platform development was originated. So let's see what it is actually is. So, cross platform development is the practice of developing the software products or services for multiple platforms or the software environments like iOS, Android, and Windows. So, engineers and developers, they use various methods to accommodate the different operating system environments for one application or product. So, they don't have to create a new application for every different environment. So the basic idea behind this is like this, that a software application or a product, it should work well in more than one specific digital habitat. And so this capability is typically pursued in order to sell software for more than one proprietary operating system, to accommodate the use on all the platforms. Usually we use the Microsoft and Apple platforms. So with the development of mobile devices and the other kinds of platforms and other operating systems, as well as with the proliferation of open source technologies like Linux, with the adoption of Linux, and there are some more cross platform developments have been emerged. And then this using this cross platform development, it ensures that the overall look of the app can be maintained across all the platforms, since using the same set of code is being utilized. And so the customers, they find an app cumbersome and inefficient if they need to use different methodologies to access the same app across different phones. So modern cross-platform development tools are one of the many development trends that make the life easier for the developers and users. And for cross-platform development, we use Xamarin. So with the development environment of Xamarin, or Google has given the Flutter technology. So software developers can write applications that work on nearly every major desktop and mobile platform. And we see that unlike the cross-platform development tools of the past years, these new technologies, sorry, these new technologies, they took the software technologies, they took the full advantage of the native apps, and they allow you to create source code. They allow you to create apps that will behave natively without sacrificing the major performance. So there are cross platforms. These are developed using the special tools that we will discuss later in this presentation. uh, so there are some specific platforms that work on it. So it cross-platform application frameworks are those frameworks that allow the developers to develop mobile applications that are compatible with different operating systems, as I discussed earlier. Mostly the operating systems that are being considered are iOS and Android, because Windows is not in demand that जितना पहले होता था. So these frameworks allow developers to write code once and run it for other platforms anywhere. So even though this cross-platform application development framework, it comes with some of the performance problems, but the developers are still opting for it because it saves a lot of money and time, and the cost of development and the specialist issues. So let's see the some of the advantages of cross-platform development. Now, as we have seen that cross-platform development, it offers the part of code reuse option. It gives you the unified logic and architecture, which will save significantly the reduce the development time. Moreover, it gives the developer high economic efficiency, which makes the development affordable even for small businesses. And the product, every product we know it has some bugs. So the product development it overcomes many bugs. So if a product has a bug to be fixed, then it is fixed for all the platforms on which the project is distributed. And the another thing is that as we have discussed this as earlier as well, it gives high launching speed, and it provides the reduced update cost. As we know that in today's market, this is a very weighty argument. The customers always require that they get the product, they get the application in a reduced time with a reduced updates cost, and reduced development time and cost. So cross platform development gives you this advantage of using it. But however, there are some of the advantages as well. uh, as we see that there's shared code based among iOS and Android. So shared code based apps are not always seamlessly integrated into the platform. So it may make the user experience equally good for all operating systems. It is not that easy. Moreover, cross-platform apps are not well integrated with the OS as native applications work, which may affect the performance and speed. And they may be limited access to the platform's unique features and device functionality. So it may not be that efficient. But in most cases, these disadvantages become irrelevant if the project is being developed by some highly skilled professionals. So then you will consider, then you will definitely use cross-platform development. For example, the framework Xamarin, it will allow you to easily interact with the device native functions as well. It will help you to use the necessary device functions API interface as well. So now the question comes which one to use, either native or cross-platform development. So let's see each of these options, which one is right for your project, which will depend upon its pros and cons, because each of these options has its pros and cons as we have discussed earlier. So the choice between cross-platform and native development should be made depending upon the required functionality by the application and the application's implementation area. So it is impossible to give a universal answer to the question that which one is better, since it varies case to case. So, however, from a technical point of view, if you consider it in terms of user experience priority, native applications have some more advantages. However, there are quite a few situations where the appropriate choice becomes the cross-platform solution. So, you will make a choice in favor of native application if your product requires full access to hardware features and OS capabilities, and when you require maximum efficiency when using device hardware capabilities. For example, if you have if you have to do processing of large volumes of data on the client side, and you will make it a choice if you have to develop utilities that manage system resources. However, when the product must provide the highest possible quality of user experience, then you will go for native application. And cross platform becomes an excellent choice if you need to quickly enter the market to test your data under the real life conditions. And it's actually about developing a business to business solution. So whenever Deployment speed is important, then the way it looks, then you will use cross platform development. Most importantly, you will use it when you need to create an application for several platforms given a limited budget. And also you will make it a choice when you want to need to make a client app for a website or for any other product which does not involve any complex functionality. However, you do need to consider some long term perspectives because they do matter. You never know how things will be moving. You have to always look on your long term perspectives and objectives, so it is worth taking thinking about the strategy in terms of those perspectives in the long run. So let's see some of the cross platform application frameworks. The first framework that we encounter is Ionic. Ionic is an open source cross platform framework which is licensed under MIT. This has a similar design to AngularJS, if you are familiar with AngularJS, and it can be used to build some native like hybrid apps and progressive apps. Developers usually love this framework because of its lovely features and design elements. Then we have Xamarin. Um, Xamarin is very famous platform. It is also a cross platform framework. Now it is owned by Microsoft, and it allows the developers to create some native Android and iOS applications using C Sharp. So the applications built with Xamarin, they do not have any performance issues because the applications are compiled before they are using they are used, and only one user interface is designed separately. And then we have the third framework, which is React Native. All of you might be familiar with this React Native as well. It is very commonly used. It is also open source, and its popularity has increased a lot. So this framework allows developers to use code using JavaScript. So it reduces the learning curve because we are familiar with JavaScript. So mobile application development usually uses it because it reduces the development time as well. The latest technology that we have encountered is Flutter. It is also an open source free framework which is launched by Google in the past years. So developers love using Flutter because it helps them in faster development, and it allows to preview the code within the device. Then we have Adobe PhoneGap. So it is also a cross-platform application development framework which is owned and sourced by Adobe that makes use of HTML5, JavaScript, and CSS. So like all other cross-platforms, it also allows developers to preview results within the same device so that they can make the code changes there. So with PhoneGap, developers can share the app with their team to get the feedback. So these frameworks can be used if you have to do the cross-platform development. When you use Xamarin, you can use Xamarin Forms. It gives you the library of templates that will help you use the standard interface elements. So whenever you have to develop any application for iOS, Android, Windows, whenever you have to build any application, if you do it separately, that becomes time consuming, expensive, and lots of engineering efforts is there. But if you use these frameworks, then this it will not be time consuming. It will reduce your engineering efforts, and it will help you a lot. So in this way it summarizes my work, this talk. Whenever your businesses, they will opt for cross platform application development because of this, its cost effectiveness. It gives you high return on investment. It gives you short term time to market. It gives you the companies can get the best of both worlds with a very minimal cost. So you can use the cross platform frameworks for your work to speed up your work. Thank you so much, everyone. If you have any questions, I am here to answer. Over to you, Farwa.
Thank you so much, Dr. So much, Dr. Machines, for such a valuable talk. Let's call our next speaker, Dr. Numan Nazir, Air University, Islamabad. He is a senior member of IEEE, Head of Neurorobotics Research Group, Department of Mechatronics Engineering, Air University, Islamabad, and Vice President of IEEE Robotics and Automation Society, Pakistan. His PhD research was supported by a world-class university program funded by the National Research Foundation of Korea. Dr. Nasreen has published over 75 peer-reviewed papers and has received more than 1,800 citations from all around the globe. He is also the founder and CEO of two companies, Alpha Automation and Time. So please join Dr. Numan Nasir.
Bismillahirrahmanirrahim. Assalamu alaikum. I hope I'm well audible.
Yes, sir, you are audible. Please continue.
Okay, thank you. Thank you very much. So, I'll be talking about neurorobotics and robotic rehabilitation. I'm Noman Nasir, the head of Neurorobotics Research Group at Air University, Islamabad. And what I do is I work in controlling external devices and robots through brain signals. So this is the presentation outline. I'll just introduce the audience with brain-computer interfacing, a little about human nervous system, then I'll go to prosthesis and the control of prosthetic devices using human brain. Well, brain-computer interfacing was a term coined many years ago. It was in 1924 when for the first time, this German scientist, Hensberger, basically recorded for the first time human brain activity or the electric current flowing through human brain. It was recorded before in animals, but in 1924, that was the first time humans were used as subjects. So what happens is that when we think of doing something, our central nervous system generates some commands and sends those commands to the peripheral nervous system. In this photo, you can see this pink colored thing is consisting of the central nervous system, and these blue things are the peripheral nervous system. So control commands are generated here. They travel through the spine to the peripherals, and you can control your limbs. However, if for some reason someone gets amputated, what we can do is we can get the signals from his arms, shoulders, etc., and control the robotic arm. We don't need to get the signals directly from the brain because the signals still muscles are coming fine. So what we do is what we call muscle-based control or EMG-based control, electromyography-based control. So this is essentially what we want to do in this case. You can see in this video, we have placed some sensors on the human arm, and a robotic arm is trying to mimic what the real human arm is doing. Of course, there has been a lot of research going on in this topic, and we have developed some excellent prosthetic arms, and I'll show you in the next slide, which can work not as robustly as a real arm, but quite near to what a real arm can do. So this person can grab a ball, some things. He can do his daily life works using this prosthetic arm. So his right arm is a robotic arm, and all the sensors, batteries, wiring is inside this patch, which is placed on the shoulder. So this is one classic example of neurorobotics which we want to do. So we tried to replicate this work many years ago, 7 years ago, and there was a student, an undergraduate student, first semester undergraduate student, and he said that he wants to do so, and he made a robotic arm using ice cream sticks and some motors, and they developed a mimicking mechanism. You can see the motion of the elbow joint and the wrist joint, and both elbow and wrist joints. This system was actually made in less than 2,000 Pakistani rupees using things from just junkyard. Then as we grew up as a research group, we bought some sophisticated sensors. This sensor here is called Myo Arm Band. It grabs the muscle activity and wirelessly transfers it to a processing unit, a laptop. And this laptop is then used to classify those signals into different control commands, which is then sent to the robotic arm, which we manufacture, prosthetic arm in this case, and it can be controlled. So in this video, you can see there's a little problem. The problem is that the gestures are different and different fingers are moving. So we are controlling different fingers of our prosthetic arm using different gestures. However, that's not what we want to do. What we want to do is that we should be moving our index finger and the robotic arm should be moving its index finger as well. The pattern recognition becomes more complex in this case, but we tried it next year and my undergraduate students completed it. There was still some errors, but I mean, the system was more than 90% accurate. So this is the MyOne band, which acquires the muscle signals. These signals are sent to MATLAB or Python in our case nowadays. And then we perform machine learning in this platform and send the control commands to the external device, which is prosthetic arm in this case, prosthetic hand in this case. This is the thumb motion. This is the little finger. The middle finger. Ring finger, and so on. So of course, there were some misclassifications as well, but the accuracy overall was above 90%. This was done back in 2018 by undergraduate students. So I was telling you the examples in which, of the case in which the robotic hand is required because the regular human arm is amputated. However, in a case when the spine of a person is injured, in that case, the brain will be generating the signals, but those signals won't be able to travel to the peripheral. So in that case, we are left with no option but to acquire signals from the brain directly. So in such cases, we perform brain-computer interfacing. So we make a brain-computer interfacing system, we acquire signals from the brain and send them to an external device for controlling purpose. It could be a robotic arm, prosthetic arm, a wheelchair, anything. So this is a block diagram of the brain-computer interface systems. What we do is we first acquire the signals from human brain. How do we do that? I'll tell you in the later slide. We process those signals. We perform some feature extraction to decode those signals, and then classification. And based on the classification results, we try to do the application interface. Application could be anything. To acquire brain signals, we can use different methods. One of the methods is to open up the brain and skull and insert the electrodes inside the brain. That's called the invasive method. It was done back in 2006. This person, Matt, he was a famous basketball player. And one night he was coming back from practice when there was a robbery attempt on him. He tried to resist, and those burglars, they actually stabbed him in the back. His spinal cord neuron was gone, and he was neck down paralyzed. So we inserted this chip in his motor cortex, the cortex of the brain, which is responsible for motion. And using the signals acquired from this chip, we controlled a cursor on a screen for him, so he could use his emails, reply back. So you see, if we can control a cursor on the screen, essentially we can control a wheelchair. We can develop a GUI which can be used to control a wheelchair. Then the next work we did was in 2007, which was published in Nature in 2008. It was back in, used to be in University of Pittsburgh. So what we did was we grabbed a monkey and implanted electrodes in its brain. We did not feed him for quite some time, and then we knew what he's going to do when we put a feeder in front of him. So you can see in this video, this monkey is using a prosthetic or a robotic hand to feed itself using the brain signals only. Its own hands are tied up here. We're placing the feeder at different places just to show the workspace of this robotic hand. Well, this work was done in 2008. If this was done in 2008, we should have been able to do it on humans the next year or the same year. But ethical approvals took a lot of time, and we did that back in 2012. Done by the researchers at Brown University primarily. This is what happened. So there was a lady, she was neck down paralyzed for several years, 15 years. So this lady could actually grab a cup of coffee and drink it for herself after 15 years. And that was indeed a special moment. However, when we see the results, we show you the best, results in the videos, but if you see the numbers, the results were not so encouraging. Even on the best day, the accuracies of grabbing or grasping were up to 62. Four systems is that it requires surgical procedure. It is prone to build up of scars, and those scars can become cancerous, and you need some time after recovery from the surgery as well. What we want to do is we want to acquire brain signals non-invasively. We want to have electrodes which are placed on the head and not inside the brain. So we at Air University made a system in which EEG-based wheelchair was controlled. So my students, they developed it and did it as a part of their final year project. So this person is controlling this wheelchair using brain signal. This was done back in 2017 and funded by ICT R&D, which is now Ignite. But then we thought of making another system based on home automation. So you see, the people who are paralyzed and are bedridden, or even if they're not paralyzed and bedridden for some reason, even if they have to turn on the fan or lights, they have to request someone to do it on their behalf. We made a system in which they can just wear a head cap, and using the eyeball movement detected through brain, they can turn on and off the lights and fans. This is the demo of what we did. Again, my undergraduate students at Mechatronics Engineering Department at Air University did. We also made a game control, EEG-based game control, in which we targeted the audience, like young people who want to play games and using their brain only, no muscle movement. We use this headset. acquired brain signals, processed it in the processing unit, and then send it to control a pinball game, which used to be in Windows 98, I guess. We still have lots of issues with this system because consistency is an issue. All these systems that I've shown you, even the wheelchair one, it was up to 80% accurate. Of course, until these systems are not 100% accurate, we can't commercialize them. We don't want paralyzed people to be in some kind of trouble because of misclassification, you know. And then there's lots of noise in EEG signals because the the far away you move from the source, the noise becomes more. The closer you are to the source, the noise will be less. So in case of invasive implants, the noise is less because you're closer to the source. Because of the noise, pattern recognition becomes a trouble. Then there's a system based on MRI. You must have heard about MRI and MRI-based robot operation. So in this system, what happened was there was a person sitting in an MRI machine in Israel, and he was controlling a robot in France. This is like the experience of I mean, it's like an hazardous environment. And humans can't go there. So put themselves in some machine and control the external devices. So So this kind of systems can be made as well. Then we made a lower limb rehabilitation system. And this system, where we later tried to make it a brain control system. Right now, you can see someone is turning on and off using a button or switch. But later we made a system which could be turned on and off using brain signals. This was a system that we made, which is turned on and off using brain signals, FNIRS-based control. It was published in the best journal of our field. We also made some FNIRS-based brain-computer interface systems, some sensors, which can be used to measure the brain signals. This is one such sensor which uses near-infrared light to measure the brain activity, what's going on. And using that sensor, we actually performed hand opening and closing of a robotic hand. Then we also did some binary decision decoding things in which there was a person who was in vegetative state back in South Korea. He had a neuronal degenerative disease. He was in a state of coma. I mean, all his inputs were working, but none of his output was working. He could see and listen to us, and process it in his brain as well, but he could not respond even with a blink of eye. So we made a decision decoding system in which we asked him to perform one brain activity if he wants to answer in yes, and another brain activity if he wants to answer in no. And we tested this system, and he could actually communicate with us. We extended this system to multiple choice question decoding next year, again published in a best journal of our field. Then we made a lie detection system. Based on the previous two works, we thought that it would be possible to make a lie detection system. And we found out that the neural correlates of telling the truth were different than those of telling the lie. The conventional system which is being used uses some biological biosensing, I mean, the sensing of heart rate, eyeball movement, amount of moisture on the body, etc. But we complemented the previous system with brain signals as well. So it was not easy to fool the brain, actually. It's quite easy to fool the body, but not brain. Then a drowsiness detection system was made. This drowsiness detection system was actually implemented in a Hyundai Motor Company trucks in South Korea. We also made a heart disease detection system using ECG machine. So automatic heart disease detection system, which could detect 5 most common diseases out of 25 or more, which can be detected using ECG. Alhamdulillah, all these works resulted in publishing 2 book chapters, 24 journal papers, and 52 conference papers in last 5 years only. We have international collaborations with, I mean, many professors of the field, 7 or 8 different countries. This is the team of my students who work with me. We have been to many local and international competitions and won several awards. In 2018, a special moment for us in Pakistan was when we won the Bill Gates Foundation Award, won 10 million US dollars, alhamdulillah. It was a special moment, of course. This is my team. When we started back in 2015, we were just few people, and alhamdulillah, we have come a long way from there. Thank you very much. That's all from my side. If you have any questions, please let me know.
Thank you so much, Dr. Numan Nasir. It's an honor to have a day with us and such a valuable talk. Thank you so much, sir. Let's call our next speaker, Dr. Arif Mahmood. His PhD in computer science from Lahore University of Management Science. His PhD thesis was on computational elimination algorithm for correlation-based fast template matching. His major area interest including data clustering, classification, action, object recognition using image sets. He has also worked on computational elimination algorithm for fast template matching, video compression, and object removal and image mosaicing. So I requested Dr. Arif Mahmood to please join.
Yes, thank you. Thank you very much for introducing me. So let me share my screen. Just a moment, please. Yeah. So, right. So is this, so my screen is visible to everyone?
Yes,
Hello?
sir, it's visible.
It's visible. Yes, thank you. Right, so let me introduce myself. I am second in this line, and my name is Arif Mahmood. Currently, I am working as a professor in Information Technology University, Lahore. Right, I joined this university 2 years back as associate professor, and recently I have been promoted to full professor. Right, I'm working in computer vision and machine learning areas. So today I will present my paper in European Computer Vision Conference. This was presented few months back in ECCV 2020. These are my collaborators in this paper. First author, Mr. Zegam Zahir is PhD student. Second is mine. Third, Astrid is also a PhD student. And fourth, Sangek Lee is the Korean professor in ETRI and UST. So it's a collaboration with these two institutes, UST, University of Science and Technology, South Korea, and Electronics and Telecommunication Research Institute, South Korea. This work is regarding anomalous event detection. It's a research project being carried out in ETRI. So let me move forward. So what is abnormal or anomalous event? It's generally difficult to define. So maybe someone can think that the dog here is an anomaly. It should not be here, but someone can think it's perfectly okay. The definition of anomaly varies. Like it could be anomalous to someone and not anomalous to someone else. Similarly here, fire inside a heater is perfectly normal, but fire outside that could be very, very anomalous and very dangerous as well. So if we detect fire, it won't be enough because it could be a safe fire. Similarly, we have a normal crowd and we have an abnormal crowd, but automatically detecting it could be quite difficult, right? So how we can then detect anomalous events automatically? So our motive is if something unusual happens, we should detect it immediately. It's difficult to obtain examples. Like abnormal things don't happen every day. These are abnormal, so these happens once in a while after a long time. Therefore, weakly supervised algorithms are popular. Weakly supervised means we have very limited supervision. We don't know much about anomaly, but we know much about normal things. So we do training on a normal class and then do testing. And during testing, we separate abnormal class from the normal. This is generally used one class classification thing. We train one class classifiers that only know about one class. If something other than that class happens, then our classifier can tell that this thing is not from the current class. Right, so what means weakly labeled trainings? Weekly label training means that we have labels. For example, in our case, our labels are video based. We don't have frame level labels. So we have a complete video that contains normal and abnormal things, and we label it as abnormal, and then try to use this supervision for frame level identification of abnormal events. So there are many advantages of weakly labeled annotations. So because frame level annotations are very hard to obtain, it takes lot of time to label each frame. So like in this example, you can see some normal event, then an abnormal event, and then an other normal event. Frame level. So these labels are frame level. And in case of video level, we only call this video as anomalous, and it's a weak label. If we have frame level labels, then it's a strongly supervised, because we exactly know. So this is our data set. We have some videos completely normal, some videos having abnormal chunks in them, and then we label the normal ones as 0 and abnormal ones as 1. So this is weak labels. So we need to develop some kind of reasoning by using these weak labels. These are different from, so anomalous may be different and the normal may be similar. So it could be one clue that whenever there is something normal, it is similar, but whenever there is something abnormal, it will be different. Right, so this is an example of theft, where someone comes in and grabs and then runs out. And we have to detect that this was something abnormal, right? So what we do is a batch-based training. So first we use a feature extractor. We extract features from different videos, and then using these features we make batches, and our batches are random batch selectors. We make a random selection of batches. So what batch means, like 15 frames of each video is a batch, and then batches are extracted from different videos. If it comes from an anomalous videos, we will treat it as an anomalous batch, and if it comes from a normal one, then we treat it as a normal batch. Right, then we train a neural network, and this neural network primarily tries to identify if this batch is from a normal or an abnormal video. So of course, we don't expect to get very good results from this neural network, because our labels are faulty. Many normal things are also labeled as abnormals, but we are sure that when we call something as normal, then it is perfectly normal. So on that side, like on the normalcy side, we are sure, but on the abnormal side, we are not sure, because we are just labeling these chunks as abnormal, even if they could be actually normal. So anyhow, we train this backbone and we use this random batch selectors. So the usefulness in this problem of randomness is huge. Like we get, even with this very naive approach, accuracy very similar to state-of-the-art accuracies. It was because we have broken the correlation within a video. So when we show this network chunks from different videos, then each chunk is uncorrelated with its predecessor. So this way we have broken the correlation. So breaking correlation was very helpful in this problem. To further strengthen this network, we use the normalcy suppression module. So normalcy suppression module is like attention. So we use two levels of attentions here. So at first level, at the first layer, and at the second level in the second layer. So we have only two layers in this network. So on both layers, we put this attention module, which we call as normalcy suppression module. Right, so even with this normalcy suppression module, what we try to predict a score at the end. If it is 1, if the score is 1, that means the input was anomalous. And if this score was 0, then we call it as, then we call that input was a normal thing. Right, so we further strengthen our system by a clustering algorithm. So this is perhaps among very few works which use clustering to strengthen a neural network. So clustering is unsupervised, right? So we use k-means clustering here, which is quite simple approach. By using k-mean clustering, we strengthen our network, and network strengthens k-mean clustering, like it's a bidirectional process. So what happens? We get features from the first layer of the network, FC1, and we apply k-means clustering, and we cluster whatever we get, the data belonging to each video, into two clusters. Right, so if we know that the video was normal, then we try those clusters to be as close to as possible to each other. But if we know that the video was an abnormal video, then we believe that abnormal frames must be somewhat different from the normal ones, and we try to pull these two clusters away from each other. So we train networks such that these two clusters become away for the case of abnormal videos, and we train networks in such a way that if the video was normal, then these two clusters should come close to each other. So this signal goes to the objective function of the network. So by using this simple approach, we get a boost in our accuracy. The network is enabled to identify which of the chunk was abnormal and which was normal. To achieve the desired targets, segment level. So it's a segment level prediction by utilizing the limited amount of information available, that is video level labels. Losses are computed at 3 different levels. So we compute loss at segment level, at batch level. A batch consists of 64 segments, and then at video levels. So at 3 levels we compute loss, and we apply these 3 levels simultaneously to our neural network. The segment level loss is regression between the segments prediction and the video level label. So one loss is just the regression between whatever label we get from the video, which of course is not very correct, and it's a weak label. These labels are noisy but help implicitly in the learning process. Then we apply temporal smoothness. So temporal smoothness simply means that if current chunk was normal, then next should also be normal. And if current was abnormal, then next should also be abnormal. It's like things should happen smoothly in time. Yeah, another loss we apply is sparsity loss. Sparsity loss simply means that abnormality happens once in a while. So most of the times our labels should be 0, and very few times it should be 1. So we suppress labels in a way. We try to get all zeros and only 1 if we are pretty sure that there was something abnormal. And then the clustering loss. So what we do, if the video was normal, then we put the distance between the two clusters within the objective function. And we try to minimize that for the normal case. And if the video was normal, then we put 1 over distance, like inverse of distance in the objective function, because we want abnormal to be away and normal to be close, and we are minimizing our objective function. Right, so this is a comparison with the state-of-the-art approaches on the same problem. These all approaches are published in very prestigious venues like CVPR, Computer Vision Pattern Recognition, and ICCV, ECCV, or PEMI. Some of them are from PEMI. So, and these are these approaches are recent ones published in 2019 or at least after 2015. So BBN is our basic approach where we have only basic backbone network. Then BBN with random batch selector. So BBN obtains 69.5% accuracy, but when we add random batch selector, so which I told that we break the correlation within a video, which previous works have not done. So simply breaking the correlation gives us a boost in accuracy. Then we add the normalcy suppression module, which is in a way attention module at 2 levels. So normalcy suppression module is at 2 levels at the first layer and second layers. So both addition of those gives further boost, and then we add the clustering loss, and by adding the clustering loss, clustering aware weakly supervised network. So this is the name of our system, ClassNet. So you can search our system by ClassNet on internet. We have put a video on YouTube and I've also made a GitHub page. Right, so the second column is feature types. C3D feature is a well-known feature which take 16 frames of video and convert it into a single feature vector. It incorporates the information of motion and appearance both. So these are spatiotemporal features, C3D features. So by using all these things with neural network, we get 83.03 on UCF crime dataset. So UCF crime dataset is the biggest real world dataset available for anomalous event detection. It has a lot of crime categories like theft, fight, or burglary, or like these. And it's very hard to automatically detect when it happens. So when we report our accuracy, we report at frame level. Like we compare the ground truth at frame level, it's only available for test sequences. So they give splits of training and test, right? So in the training, we don't have frame level annotations. In test, we have frame level labels. So by using those frame level labels, we compute accuracy. So up till now, we in our further work, we improved from this figure 83.03 to 85. But in this paper, our best accuracy was 83% on this data set. Right. So now I will briefly discuss different parts of the system. So the important parts of the system are normalcy suppression module. So this is output of the first normalcy suppression module, the longer one, and the smaller one is the output of second normalcy suppression module. The first one is more important because here we have more data, and the second one is less important, but of course it also contributes in the system performance. So what these modules do, they try to suppress the result of a normal video. If we get a normal video, these modules try to make the output of the chunks of normal video to 0. And in case of abnormal video, they do nothing. Like it's inverse of the attention. So in attention, we highlight some portions of a video which are more important. But here we do inverse. We suppress the unimportant parts of the video, which we know for sure that these are unimportant. So this part of network then learns what is unimportant. So it's inverse of attention. Therefore, we named it as normalcy suppression. But one may think it like a type of attention, right? So the bright spots here, these are the normal things, and the dark spots are, the bright spots are abnormal things, and the dark spots are normal things. So normal is not important, and abnormal is important because we are after abnormal things. Similarly, high scores in these graphs, they show anomalous regions. So in anomalous regions, we get high scores in these modules. But these modules individually are not enough for getting good accuracy, right? So here we show the anomalous segment. Within anomalous segments, we get higher values, but outside that, most values are small. So these are the anomalous regions, and then outside are the normal regions. So these graphs show that these two modules, they were able to identify the anomalous regions in the video with only the video level labels. Right, so this is further visualization. So we get, so here is an explosion. So we have one explosion category in the data set, and then normal category. In case of normal, you can see all values are small. There is no bright spot. Vandalism, in case of vandalism, you can see like the top one is vandalism. Is last, in the last there is a anomalous thing. So in the anomalous region, we see these bright things. So by using this approach, we can identify crimes in the surveillance cameras. It's like pretty hard thing, but fortunately we are getting very good results in it. So these are the final results of the system. The system generates for each chunk of video one score that we call as anomaly score. If that score is high, if it's close to 1, then there will be something abnormal. And if it is close to 0, then things are normal. We plot that score on the time axis. So x-axis is time, y-axis is anomaly score, and when anomaly score is higher, then this highlighted region, this region is the anomalous region. So in this region, you can see mostly our score gets higher, and in normal region, which is white. So first one is shooting sequence. Some shooting happens, and when shooting happens, then there is no audio in these dataset. We are only using visual things. When shooting happens, then only in that case our score is higher. The other graphs that are BBN always remains high. Then there is BBN plus RBS, BBN plus RBS plus normalcy suppression, and the red one is the final overall system response. So system response is pretty good. In case of explosion, again is high, and you should keep in mind that it's only visual data. There is no audio. We don't listen anything. We don't hear the explosion. We don't hear the shooting, but we just see that something happens. Then burglary happens. It's the most difficult thing, but we were able to identify in many sequences exactly when burglary happened. Normal, in normal things, you see very low score. Then again normal, and in case of explosion here, explosion 008, the ground truth was only up to this dark region, but after the explosion there was emergency and there were ambulances around. So therefore our system still marked the remaining time as abnormal time, although in ground truth it was not abnormal. That's why our score is not 100%, because the ground truth is not true. It's not, maybe someone who marked the ground truth in University of Central Florida, he considered after the explosion as normal, but it was not normal. Still there were lot of emergency things happening. Right, so this is the last page of my results, and we did publish a similar work in IEEE signal processing letters, and before that one work was published in CVPR 2020 as well. That was one class classifier, and we are extending that for IEEE transactions on pattern analysis and machine intelligence, PAMI. We plan to submit that work in PAMI. Right, so this was from my end. I will welcome any questions or any suggestions. Let me break it. Yeah, hello. Any questions from the audience?
Thank you so much, Dr. Arif Mahmood.
So is there any question from anyone?
Thank you so much, Dr. Arif Mahmood.
Yeah,
It's an
thank you.
honor to have a day with us. Thank you, sir. So, ladies and gentlemen, we will have a short break and rejoin the session at 11, inshallah. 11:15.